What if I told you that colonizing Mars is easy, but reaching the nearest star may be almost impossible? Mars can come as close as 55 million kilometers from Earth, a journey of just 7 to 9 months using a Hohmann transfer orbit. Proxima Centauri, our nearest stellar neighbor, is 4.24 light-years away, about 40 trillion kilometers, roughly 700,000 times farther than Mars at its closest approach. One destination is difficult but within engineering reach. The other pushes against the limits of physics itself. Tonight on Velorin Sleepy Space Mysteries, we'll gently explore this contrast, not through hype, but through numbers, scale, and quiet perspective. By the end, you may never look at the night sky the same way again. If you enjoy calm, thoughtful journeys through the cosmos, subscribe, like, turn on the notification bell, and consider joining our membership to support deeper explorations. And before we continue, tell me in the comments where you're listening from. Let's see how far this signal travels across Earth. Now, let's begin. Mars does not wait for us at a fixed distance. It moves, just as Earth does, tracing its own long ellipse around the Sun. At its closest approach, during opposition, Mars can come within about 55 million kilometers of Earth. At its farthest, when the Sun stands between our worlds, the distance stretches beyond 400 million kilometers. That variation sounds dramatic, but it follows a predictable rhythm. Roughly every 26 months, Earth and Mars align in a way that opens a quiet window, a launch opportunity when fuel requirements are minimized and trajectories are efficient. During those windows, a spacecraft can follow a Hohmann transfer orbit, a graceful curved path that arcs outward from Earth's orbit to meet Mars where it will be, not where it is now. Using this method, the journey takes about 7 to 9 months. Not years, not decades, months. 7 months is long enough to feel substantial. It is longer than most pregnancies. It is far longer than the Apollo 11 mission, which carried humans to the moon and back in just over a week. And yet, 7 months is something we already understand. The Perseverance rover launched in July 2020 and arrived at Mars in February 2021. About 7 months in transit. We have repeated this timeline many times with robotic missions. The physics are known. The trajectory is mapped. The duration is measured in seasons, not generations. A human mission would begin quietly, not with a single dramatic launch, but with assembly in low Earth orbit. Components would rise separately: a crew vehicle, a propulsion stage, and a transit habitat. Piece by piece, they would dock together above Earth, circling every 90 minutes in the familiar safety of our planet's magnetic shield. The crew would launch last. They would float through a docking tunnel into the assembled spacecraft that will carry them outward. The transit habitat would not be enormous. It would be roughly the size of a school bus, compact, efficient, carefully arranged. Sleeping quarters no larger than closets. A small galley, exercise equipment bolted to the floor and walls. Workstations glowing softly. 4 to 6 astronauts would live here for 7 months, following structured routines. Exercise would be mandatory 2 hours each day to counter muscle loss and bone density reduction in microgravity. Maintenance tasks would fill the hours. Scientific experiments would provide purpose. Outside the windows, Earth would shrink to a pale blue star and then disappear. Water would cycle constantly through the system. The International Space Station already recovers over 90% of water from urine, sweat, and humidity in the air. For a Mars mission, that number would be pushed even higher. Every drop would be reclaimed, filtered, purified, and reused. This is not speculation. It is refinement. The technology exists. It must simply become more reliable, more redundant, more autonomous. Air would be maintained through stored oxygen reserves and carbon dioxide scrubbers. The exhaled breath of the crew would be cleaned and recirculated. Some mission designs include small plant growth systems, not vast gardens, but enough greenery to supplement nutrition and refresh the atmosphere in modest ways. Food for a crew of 6 over 7 months would weigh several tons, including packaging. That sounds large, but compared to the mass of a rocket, it is manageable. Prepackaged meals would form the core supply, similar to those already used in orbit. Fresh vegetables grown on board could provide psychological comfort as much as vitamins. Radiation remains a serious concern during transit. Outside Earth's magnetic field, astronauts are exposed to solar particles and galactic cosmic rays. But shielding options are known. Water is an effective barrier. Polyethylene, rich in hydrogen, can absorb high-energy particles. Even stored supplies can be arranged strategically to form protective layers around sleeping areas. We cannot eliminate radiation risk entirely, but we can reduce it to levels considered acceptable for deep space missions. This is mitigation, not miracle. Power during transit would come primarily from solar panels, extending like wings from the spacecraft, converting sunlight into electricity. As the vehicle approaches Mars and sunlight weakens slightly, a small nuclear power source, such as a radioisotope generator, could supplement energy needs. Both systems are proven. Both have decades of operational history. The journey would feel long, but it is bounded. Communication delays would stretch from a few minutes to perhaps 20 minutes one way, depending on distance. That is inconvenient but manageable. Instructions can be planned in advance. Emergencies can be handled locally. Earth remains close enough to advise, to monitor, to support. Months, not centuries. Minutes of delay, not years. Launch windows every 26 months, not once in a lifetime. As Mars grows from a reddish into a disk filling the forward view, the hardest phase approaches. Entry, descent, and landing. Mars has an atmosphere, but it is thin, thick enough to create intense heat during entry, yet too thin to slow a heavy spacecraft completely with parachutes alone. Robotic missions have used heat shields, parachutes, airbags, and sky cranes. But a human lander could weigh 20 to 40 tons. That mass changes everything. The leading solution is supersonic retropropulsion, firing rocket engines while still traveling faster than the speed of sound in the Martian atmosphere. It sounds dramatic, but it has already been demonstrated on Earth by reusable booster stages returning from space. Scaling it for Mars is difficult, but difficulty is not impossibility. And this is the quiet truth that runs beneath every step of the plan. None of this violates physics. It requires engineering discipline, funding, redundancy, and courage. It requires acceptance of risk. But the equations close. The materials exist. The methods are grounded in known science. Mars is far. Mars is harsh. But Mars is within reach. As the spacecraft approaches Mars after 7 steady months, the planet does not rush toward the crew. It grows slowly, almost politely, from a rust-colored point into a world with visible polar caps and faint surface markings. The transition from transit to arrival is not cinematic. It is procedural. Calculations are checked and rechecked. Trajectories are adjusted by small engine burns measured in seconds. Every movement is deliberate because once entry begins, there is no turning around. Mars entry is a study in balance. The atmosphere is thick enough to generate tremendous heat as a vehicle slams into it at interplanetary speed, yet too thin to provide the comfortable braking that Earth's atmosphere offers returning spacecraft. A massive heat shield absorbs the plasma glow of friction. Behind it, the crew waits in a controlled environment while the outer layers endure temperatures of thousands of degrees. After peak heating, parachutes may deploy, but for a lander weighing 20 to 40 tons, parachutes alone are insufficient. This is where supersonic retropropulsion becomes essential. Engines ignite while the vehicle is still traveling faster than sound, pushing against its own momentum, carving a controlled path downward through the thin air. The technique is demanding, but it is rooted in physics we already use. Rockets slow things down in space. They can slow them down in an atmosphere as well. The landing site would likely be near the equator, where temperatures are relatively milder and sunlight is more consistent for solar power generation. Ideally, robotic cargo missions would have arrived earlier, delivering habitats, power systems, drilling equipment, and ascent vehicles long before humans ever left Earth. The first human footsteps would not mark the beginning of construction, but the continuation of preparation already in place. Mars would be waiting with tools ready. Power comes first. Without energy, there is no life support, no communication, no science. Solar arrays unfold across the regolith, angled carefully to capture weak sunlight that reaches only about half the intensity experienced on Earth. Dust will accumulate over time, so cleaning systems must be designed. In addition to solar panels, a compact nuclear reactor could provide continuous baseline power, unaffected by dust storms or seasonal changes. The combination of solar and nuclear offers resilience. Redundancy is survival. Initially, the crew might live inside the landed vehicle itself, using it as a pressurized habitat while additional modules are activated. Inflatable structures could expand outward, creating larger living volumes once pressurized. The goal is not luxury, but stability. Earth normal atmospheric pressure, filtered air free from the fine, potentially toxic Martian dust, and temperature regulation capable of handling nights that can drop to -80 degrees Celsius or lower. Outside, the landscape is silent and barren. Inside, the hum of machinery becomes the sound of continuity. Water is both necessity and opportunity. While Mars appears dry at the surface, Significant quantities of water ice exist beneath the soil at many locations, particularly in mid-latitude and polar regions. Drilling systems delivered in advance would extract ice from below the regolith. That ice can be melted, purified, and stored. It becomes drinking water, hygiene water, agricultural water. It also becomes something more strategic. Through electrolysis, water can be split into hydrogen and oxygen. Oxygen supports breathing. Hydrogen becomes a key ingredient in fuel production. The Martian atmosphere, though unbreathable, is not useless. It is composed of approximately 95% carbon dioxide. This abundance makes in situ resource utilization not a theory, but a practical plan. Using the Sabatier reaction, carbon dioxide from the atmosphere can be combined with hydrogen to produce methane and water. Methane can serve as rocket fuel. The water produced in the reaction can be recycled back into the system. In simple terms, Mars provides both oxidizer and carbon source for propellant manufacturing. Instead of hauling return fuel across tens of millions of kilometers, astronauts can manufacture it on the surface. This is perhaps the most critical step in the entire architecture. A return to Earth requires ascent from Mars, rendezvous in orbit, and another 7-month journey home. To launch from Mars, fuel must be available. That means months of production before departure. While the crew conducts scientific research, tests habitat systems, and explores the surrounding terrain, automated chemical plants quietly convert atmospheric carbon dioxide into methane, storing it in tanks for the future ascent vehicle. This is not speculative chemistry. It is industrial process engineering adapted to another world. The mission timeline reflects orbital mechanics. After arrival, the crew cannot depart at any moment of their choosing. They must wait for the next favorable alignment between Mars and Earth, which occurs roughly every 26 months. Accounting for transit time, a typical surface stay could last around 18 months. This is long enough to experience seasons on Mars, long enough to test the sustainability of systems, long enough to prove that humans can function not as visitors, but as temporary residents. During this stay, communication delays fluctuate between a few minutes and over 20 minutes one way, depending on the relative positions of Earth and Mars. Conversations require patience. Commands cannot be issued in real time, but support remains possible. Earth can send guidance, software updates, procedural advice. Resupply missions can be planned for future windows. Rescue, while extraordinarily difficult, is not beyond theoretical reach. The connection to Earth persists. Life on Mars would be structured and disciplined. Daily exercise remains essential to counter reduced gravity, which is about 38% of Earth's. Psychological health requires routines, meaningful work, shared meals, and occasional moments of quiet reflection under a pink sky. Outside the habitat, the horizon curves gently under a thin atmosphere. Dust devils may wander across the plains. The sun appears slightly smaller, but still warm. Every challenge on Mars can be traced to engineering. Radiation can be mitigated further by burying habitats beneath regolith, using the soil itself as shielding. Food production can gradually expand with hydroponic or controlled environment agriculture systems. Power grids can be reinforced. Habitats can multiply. None of these steps require rewriting the laws of thermodynamics. None demand breakthroughs in fundamental physics. The mission is difficult. It requires coordination across nations, industries, and decades of planning. It requires accepting risk. But the distance is measured in tens of millions of kilometers, not trillions. The travel time is counted in months, not lifetimes. The communication delay is minutes, not years. Mars is harsh, but it is accessible. It is a dream that rests on extension of what we already know, not abandonment of reality. And as the months on the surface pass, fuel tanks slowly fill, habitats grow more stable, and human presence becomes less like an expedition and more like a foothold. The return window approaches, predictable and patient, just as it always has. As the return window approaches, the mission shifts from settlement to departure. The ascent vehicle, prepositioned and patiently waiting near the habitat, has been slowly transformed from an empty shell into a fully fueled spacecraft. Tanks once inert are now filled with methane and liquid oxygen produced on Mars itself. The chemical plant that has been operating quietly for months has done its work, drawing in a thin atmosphere composed of 95% carbon dioxide and combining it with hydrogen derived from extracted water ice. The Sabatier reaction has converted alien air into propellant. What was once impossible is now industrial routine. This is the quiet power of in situ resource utilization. It reduces launch mass from Earth, lowers cost, and turns Mars from a destination into a participant in its own exploration. Before departure, the crew prepares carefully. Equipment that will remain is secured. Samples collected from the Martian surface, rock cores, soil specimens, possibly even subsurface ice samples, are sealed for transport. Scientific data is backed up redundantly and transmitted to Earth in advance. The habitat is either placed into standby mode for future crews or sealed as the foundation of a growing outpost. Nothing is wasted. Every mission is part of a larger sequence. When launch day arrives, the ascent is swift. Mars' gravity is only about 38% of Earth's, which means escaping its surface requires less energy than lifting off from Earth. The engines ignite, methane and oxygen combust in a controlled storm beneath the vehicle, and the craft rises through a sky tinted butterscotch by suspended dust. Within minutes, it reaches orbit. There, an Earth return vehicle, sent ahead or left waiting from arrival, serves as the final leg home. The crew transfers across in microgravity, leaving the ascent stage behind as orbital debris around another world. Then begins the second 7-month journey. The distance between Mars and Earth once again defines the path. Months, not decades. Communication delays shrink gradually as Earth grows brighter in the forward view. Inside the transit habitat, life resumes its rhythm. Exercise to preserve muscle mass, careful rationing of supplies, maintenance of water recycling systems that reclaim over 90% of every drop. The numbers remain steady and reassuring. Systems modeled after the International Space Station continue to function, refined but not reinvented. Food supplies were calculated in tons before departure. Margins were built in. The architecture anticipates failure and compensates with redundancy. Radiation exposure during the return transit remains a concern, just as it was outbound. But shielding strategies, water walls, polyethylene layers, strategic placement of cargo, reduce cumulative dosage. The total mission radiation exposure may increase long-term cancer risk slightly, but it remains within boundaries studied and understood. Again, this is mitigation, not miracle. It is management of known hazards. When Earth finally dominates the viewport, the emotional arc of the mission completes itself. Re-entry into Earth's thick atmosphere feels different from Mars. The heat shield glows once more, but this time parachutes are sufficient to slow descent. The ocean or desert landing zone awaits. Recovery teams approach. The crew steps back onto a world rich with air, water, and gravity. Rehabilitation will be necessary. Months in microgravity and partial gravity require physical readjustment, but they return with proof. Humans have traveled to another planet, lived there for over a year, and come home. This entire sequence, from assembly in low Earth orbit to return splashdown, forms a closed loop. Every stage relies on technologies either demonstrated already or actively under development. Rockets that reach orbit are routine. Life support systems that recycle air and water operate continuously in space today. Nuclear and solar power systems function reliably. Chemical reactions like Sabatier are textbook processes scaled for industry. Supersonic retropropulsion has been tested on Earth. Water ice detection on Mars is confirmed. None of this violates physics. None of it requires faster-than-light travel, exotic energy sources, or unknown materials. It requires integration, funding, and time. The emotional lens through which we view Mars matters. It is easy to focus on the danger, radiation, isolation, toxic soil, dust storms that can last for months. It is equally important to recognize that these are environmental challenges, not existential impossibilities. They are comparable to challenges humans have faced before. Crossing oceans in wooden ships, surviving polar winters, constructing cities in deserts. Mars is hostile, yes, but hostility does not equal unattainability. Consider scale carefully. The journey takes 7 to 9 months. Communication delays range from 3 to 22 minutes. Launch windows occur every 26 months. Surface days last roughly 18 months before departure alignment. These are human timescales. They fit within careers. They fit within lifetimes. If something goes wrong, Earth is minutes away by signal, not years. Resupply missions can be launched on predictable cycles. Additional crews can follow. Mars represents continuity of progress. In 1957, Sputnik orbited Earth as a metal sphere transmitting simple beeps. 12 years later, humans stood on the Moon. In 1965, Mariner 4 sent back 21 blurry images of Mars. Decades later, rovers drive across its surface and even helicopters fly briefly in its thin atmosphere. The gap between first reconnaissance and human presence is not infinite. It is generational. When humanity commits resources and attention, progress accelerates. If the will exists, Mars can be reached within a generation. The engineering challenges are formidable but finite. Each subsystem, propulsion, life support, landing, resource utilization, has a development pathway grounded in current science. Costs are measured in hundreds of billions of dollars over decades, comparable to other major national programs. Spread over time, the investment becomes manageable for coalitions of nations or even private-public partnerships. Mars is not easy in the casual sense. It is not safe in the absolute sense, but it is achievable in the practical sense. The difference between impossibility and difficulty lies in whether the laws of physics forbid the act. In Mars' case, they do not. The equations balance. The delta-V requirements are known. The energy budgets close. The materials exist on Earth and on Mars. And so, when we describe Mars as a difficult dream within reach, we are not minimizing the challenge. We are placing it in proportion. Tens of millions of kilometers, not trillions. Months of travel, not centuries. Engineering problems, not violations of relativity. A second world that can be visited, supplied, and perhaps one day settled incrementally. Mars stands as the next logical step outward, not a leap into fantasy, but a stride built upon everything humanity has already learned about rockets, chemistry, power systems, and survival beyond Earth. It is the continuation of a pattern that began with the first satellite and continued to the Moon. It is not a rupture with reality. It is an extension of it. And if you are still listening, still traveling across this quiet red landscape in your mind, type 1 in the comments. Let it mark that you have made the journey to Mars and back, and that you are ready to look farther. There is a quiet inevitability to Mars, not because it is simple, but because it fits within the arc of what humanity has already demonstrated. Each element of a Mars mission extends from existing capability rather than defying it. Rockets already lift hundreds of tons into orbit. Space stations have sustained human life continuously for decades. Autonomous probes have navigated interplanetary space with precision measured in kilometers across distances measured in millions. When these threads are woven together, the result is not fantasy. It is architecture. The deeper reassurance lies in repetition. Mars does not move unpredictably. Its orbit is known centuries in advance. Every 26 months, Earth and Mars align favorably, and every 26 months that opportunity returns. If one launch window is missed, another arrives. This rhythm builds resilience into planning. It means resupply is not a one-time gamble. It means expansion can occur incrementally. A base does not need to be fully self-sustaining from the first mission. It can grow in phases, each synchronized to orbital mechanics. Imagine the second crew arriving 26 months after the first. Additional cargo lands nearby. Power capacity doubles. Habitats connect through pressurized tunnels. Agricultural modules expand from small hydroponic racks into larger controlled environment systems. Regolith berms are piled against habitat walls to increase radiation shielding, using the planet itself as protection. What began as a landing site becomes an outpost, What was once temporary begins to feel continuous. Radiation on the Martian surface, though significant, can be managed. Without a global magnetic field and with a thin atmosphere, Mars offers less natural shielding than Earth. But covering habitats with several meters of regolith dramatically reduces exposure. Water storage tanks positioned around living quarters add further protection. Even the fuel production facilities and supply depots can be arranged strategically to create safe zones. These are spatial solutions, not speculative physics. They require excavation equipment, planning, and time. Dust storms on Mars can last for weeks or even months, reducing sunlight and coating equipment with fine particles. Solar panels must be designed with cleaning mechanisms, possibly electrostatic systems or mechanical brushes. This is maintenance, not mystery. Nuclear backup power ensures that critical systems remain functional even during prolonged storms. Redundancy again becomes the guiding principle. Psychologically, Mars presents challenges of isolation and confinement. An 18-month surface stay is long, yet it is bounded. The crew knows departure is scheduled. They know Earth remains within signal reach. Communication delays of minutes create pauses, not silence. Family messages still arrive. Scientific collaboration continues. Compared to the prospect of decades in deep space, Mars remains tethered to home. The scale of comparison matters. Months, not centuries. Minutes of delay, not years. Tens of millions of kilometers, not trillions. Rescue is theoretically possible, though unlikely in practice. Resupply is predictable. Return is planned from the beginning. Every part of the mission assumes that humans come home. That assumption shapes risk tolerance and system design. When critics argue that Mars is too hard, they are not wrong about the difficulty. They are wrong about the category. Hard does not equal impossible. Consider how rapidly progress occurred once spaceflight became a priority. In 1957, Sputnik was little more than a polished sphere transmitting radio beeps. By 1969, humans walked on the Moon. 12 years separated first orbit from another world. The gap between Mariner 4's 21 grainy images of Mars in 1965 and today's rovers driving across its surface spans decades. But within that time we have mapped the planet globally, analyzed its soil chemistry, detected subsurface ice, and even flown a small helicopter in its thin atmosphere. Knowledge compounds. A Mars mission follows this compounding trajectory. Each robotic precursor reduces uncertainty. Each test of life support systems in deep space informs reliability models. Each reusable rocket launch lowers cost. When momentum builds, timelines compress. Not because the universe changes, but because human systems align. Economically, Mars sits within the realm of major national or multinational projects. Estimates for a crewed mission often fall between $100 and $500 billion spread over decades. That number sounds immense until placed beside global expenditures on defense, infrastructure, or energy. Distributed over 20 years, it becomes a sustained commitment rather than a singular shock. Private industry contributes through reusable launch systems, in-space refueling technologies, and modular habitat designs. Public agencies contribute through research, testing, and coordination. It is not trivial, but it is plausible. Mars also offers return on investment within a human lifetime. Scientific discoveries about planetary evolution and potential past life. Technological spin-offs in recycling systems, power management, robotics, and materials science. Inspiration that reshapes education and innovation. Unlike interstellar missions whose outcomes lie centuries away, Mars delivers feedback within decades. And there is something else, something quieter but just as important. Mars represents continuity of civilization rather than fragmentation. A Martian settlement remains culturally connected to Earth. Languages are shared. News travels in minutes. Trade, though expensive, is conceivable. A person born on Mars could visit Earth and vice versa. Differences would emerge, certainly, adaptations to lower gravity, to red landscapes, but the thread of identity remains intact. Mars becomes an extension of humanity, not a separate branch. This continuity reduces psychological distance. It frames Mars not as exile, but as expansion. The solar system becomes a neighborhood rather than an abyss. From low Earth orbit to the Moon, from the Moon to Mars, each step enlarges the sphere of human presence without severing connection. When we say that none of this violates physics, the statement carries weight. It means the constraints are known. The rocket equation applies, but within manageable bounds. Energy requirements are large but not astronomical. Propellant masses are heavy but calculable. The speed of light imposes communication delays measured in minutes. These numbers do not crush possibility. They define it. Mars asks for discipline. It asks for patience across multiple launch windows. It asks for systems that can operate autonomously for months. It asks for courage from those who board the spacecraft. But it does not ask us to rewrite the fundamental laws of nature. It does not require breakthroughs in relativity or exotic energy sources. It requires extension of what we already know. And so Mars stands not as a fantasy, but as a threshold. A difficult dream, yes. A dream of 7-month journeys, of habitats the size of school buses, of water recycled drop by drop, of methane distilled from thin alien air. But a dream that rests on equations already balanced and technologies already demonstrated in pieces. If humanity chooses to commit, to align funding, engineering, and time, Mars can transition from ambition to achievement within a generation. From Sputnik's beeps in 1957 to footprints on the Moon in 1969, we have seen what concentrated effort can accomplish. The path to Mars is longer, but it follows the same logic. Mars is within reach. Not easy, not safe, but reachable. It is the next step in a pattern that began when we first left the ground. And as you picture that red horizon under a pale sun, remember that every challenge there has a solution rooted in known science. The journey is measured in months. The return is planned. The physics agrees. And that is why Mars, for all its difficulty, feels inevitable. Let's slowly leave the comfort of Mars behind. Not with drama, not with despair, but with numbers. Because the universe does not shout at us. It simply presents scale and waits for us to understand it. Proxima Centauri is 4.24 light-years away. That sounds modest. For 0.24, a small number, but a light-year is not small. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. In 12 months, that beam of light crosses roughly 9.5 trillion kilometers. Multiply that by 4.24, and the result is almost 40 trillion kilometers. 40 trillion. Mars, at its closest approach, comes within about 55 million kilometers of Earth. Proxima Centauri sits about 40 trillion kilometers away. The ratio between those two distances is roughly 700,000 to 1. If Mars is a walk to your mailbox, Proxima is walking across a continent hundreds of thousands of times. If a Mars mission lasts 7 months, and you scaled that same pace by the same ratio, the journey to Proxima would take tens of millions of years. Of course, we would never attempt such a journey at the slow, fuel-efficient pace we use to reach Mars. Interstellar travel demands speed. Tremendous speed. So let's ask a quiet question. How fast can we actually go? The fastest human-made object ever built is the Parker Solar Probe. At its closest sweep around the Sun, it reaches nearly 700,000 kilometers per hour. That is an astonishing velocity by human standards. Faster than any aircraft. Faster than any previous spacecraft. Faster than anything our ancestors could have imagined. And yet, 700,000 kilometers per hour is only about 0.07% of the speed of light. At that velocity, how long would it take to cross 4.24 light-years? About 6,600 years. 6,600 years. That is longer than recorded human history. Longer than the span from the earliest civilizations to today. If such a spacecraft had launched at the dawn of ancient Sumer, it would still be traveling now, still not arrived. Entire empires would rise and fall while the ship moved silently through the dark. Maybe, you might say, Parker Solar Probe isn't designed for interstellar travel. It gains its speed by falling toward the Sun surely. If we built a craft specifically to reach another star, we could do better. Let's be generous. Let's imagine we could travel at 1% of the speed of light. That's about 3,000 kilometers per second. Around 15 times faster than Parker at its peak. At 1% light speed, the journey to Proxima would take about 424 years. For centuries, if a ship left today, it would arrive sometime in the mid-2400s. The people who stepped onto a planet around Proxima would not be the people who departed Earth. They would be descendants, perhaps 20 generations removed from the original crew. So let's push further. What about 10% of the speed of light? Now we are in serious territory. At 10% light speed, Proxima Centauri is about 42 years away. A human lifetime. An astronaut who departed in their 20s might arrive in their 60s. It is long, but conceivable. Difficult, but imaginable. There is only one problem. We cannot do it. We are not close. And the reason is not funding. It is not political will. It is not engineering refinement. It is physics. To accelerate anything, you need energy. The faster you want to go, the more energy you must supply. But this relationship is not gentle. It is not linear. Doubling your speed does not merely double the energy requirement. It roughly quadruples it. Energy scales with the square of velocity. And as you approach a significant fraction of light speed, relativistic effects begin to push the requirement even higher. Imagine a spacecraft with a mass of about 100 tons, roughly the mass of the Space Shuttle orbiter. To accelerate that mass to 1% of light speed would require on the order of 4.5 times 10 superscript 1 joules of energy. That is comparable to the total energy consumption of human civilization for months. All the electricity, all the gasoline, all the natural gas, all the nuclear power, everything humanity uses across continents, concentrated into pushing one modest spacecraft to just 1% of light speed. And remember, at 1%, the journey still lasts more than 4 centuries. To reach 10% of light speed, the energy requirement increases by about a factor of 100 compared to 1%. Now you are speaking about energy on the scale of decades of global output. And here is the part that makes the problem truly unforgiving. You have to carry that energy with you. A car can stop at a gas station. An aircraft can refuel. A spacecraft heading to another star cannot. It must bring every kilogram of fuel at launch. And fuel has mass. And mass requires more fuel to accelerate. This is the tyranny of the rocket equation. The rocket equation tells us that to achieve higher velocities, the ratio of fuel mass to payload mass grows exponentially. Not steadily, exponentially. If you want to double your final speed, you don't simply double your fuel. You may need far more than double. And when you remember one more detail, the equation tightens further. When you arrive at Proxima, you are still moving. At 10% of light speed, you would cross the entire planetary system in a matter of days. You would flash past any world without time to slow down, to enter orbit, to land. To actually stop, you must decelerate. And deceleration requires exactly as much energy as acceleration. Whatever enormous quantity of fuel you used to speed up, you must use again to slow down. In practice, this means carrying enough fuel not only for departure, but also for arrival. The fuel mass grows again. The rocket equation compounds the burden. By the time you finish the calculation, the ship is no longer mostly crew or habitat. It is mostly fuel. For chemical rockets, the kind that carry us to Mars in 7 to 9 months, the math simply does not close. To reach even a tiny fraction of light speed using chemical propulsion, the fuel-to-payload ratio becomes so extreme that the spacecraft would need to be the size of a small moon to send a modest payload to the stars. This is not a matter of better engineering. It is not a matter of waiting a decade. Chemical rockets cannot perform interstellar travel. The physics forbids it. Mars does not ask this of us. Mars asks for precision, for shielding, for recycling water and producing methane from a 95% carbon dioxide atmosphere. Proxima asks us to overturn our relationship with energy itself. And that is only the beginning. So if chemical rockets cannot carry us to another star, what about something more advanced? Nuclear propulsion has long been considered the next step beyond chemistry. In a nuclear thermal rocket, A reactor heats propellant to extremely high temperatures and expels it to create thrust. Because nuclear reactions release far more energy per unit mass than chemical reactions, the exhaust velocity can be 2 or 3 times higher. In the 1960s and 70s, working prototypes were built and tested on Earth. The technology is real. It is not science fiction. But even nuclear thermal rockets top out at exhaust velocities of perhaps 8 to 10 kilometers per second. That is excellent for reducing travel time to Mars. It could cut months from a transit across the inner solar system. Yet, compared to the thousands of kilometers per second required for meaningful interstellar travel, it is still hopelessly small. The rocket equation remains merciless. The fuel ratios remain absurd. We are still trapped inside the solar system. There is a more dramatic nuclear concept: nuclear pulse propulsion, often associated with Project Orion. Instead of a steady stream of hot gas, Orion proposed detonating small nuclear explosives behind a spacecraft, riding the shockwaves forward with a massive pusher plate. It sounds violent because it is. Thousands of controlled nuclear detonations, one after another, pushing a ship to ever higher velocity. The physics, surprisingly, works. In principle, such a system could reach perhaps 3% of the speed of light. At 3%, Proxima Centauri would still be about 140 years away. That is shorter than 424 years at 1%, but still beyond a single human lifetime. And Orion carries other problems. Launching such a craft from Earth would spread radioactive fallout. International treaties prohibit nuclear explosions in space. Engineering a structure that survives repeated nuclear blasts for years is daunting. Orion is not physically impossible, but politically and practically it stands on fragile ground. Fusion propulsion appears more elegant. If we could harness controlled nuclear fusion, the same process that powers the sun, we could create engines with exhaust velocities thousands of kilometers per second. Designs for fusion-driven spacecraft suggest velocities of 5 to 10% of light speed might be achievable. At 5%, the journey to Proxima would take about 85 years. At 10%, about 42 years. That begins to feel almost human. But there is a quiet obstacle. We do not yet possess practical, sustained, controlled fusion for power generation on Earth. After decades of effort, we are still learning how to keep fusion reactions stable for more than brief intervals. Building a compact fusion reactor light enough to mount on a spacecraft, yet powerful enough to accelerate it for years, remains a distant goal. Fusion is promising, but it is not mastered. Then there is antimatter. In theory, antimatter propulsion is the most efficient of all. When matter and antimatter meet, they annihilate completely, converting their mass directly into energy according to E equals mc squared. No chemical reaction approaches that efficiency. No fission reactor compares. An antimatter engine could, on paper, accelerate a spacecraft to a significant fraction of light speed with reasonable fuel mass. The equations are beautiful. The limitation is production. Antimatter does not occur naturally in usable quantities. We must manufacture it particle by particle inside accelerators. The total amount humanity has ever produced is measured in nanograms. Billionths of a gram. To fuel even a modest interstellar spacecraft, you would need kilograms or tons. At current production rates, that would take timescales longer than the age of civilization, and the cost would dwarf global economic output. Antimatter propulsion is not forbidden by physics, but it is so far beyond our industrial capacity that it might as well be. One proposal steps around the fuel problem entirely. Instead of carrying energy on board, you leave the energy source behind. Breakthrough Starshot envisions gram-scale probes attached to ultra-thin reflective sails. A massive ground-based laser array, delivering on the order of 100 gigawatts of power, would focus light onto the sail, pushing it to perhaps 20% of the speed of light in minutes. At that speed, Proxima is roughly 20 years away. The probe would fly through the system at extraordinary velocity, taking images and transmitting data back to Earth. The physics is plausible. The components exist in early form, but there is a quiet limitation. The probe does not slow down. It does not enter orbit. It does not land. It flashes through and continues onward forever. It is a flyby, not a visit. For human travel, a flyby is not enough. We would need to decelerate, and deceleration reintroduces the energy burden we tried to escape. Even if we solved propulsion, another number waits patiently in the dark: communication delay. Proxima is 4.24 light-years away. A message traveling at light speed takes 4.24 years to arrive. A reply takes another 4.24 years. A round-trip conversation spans about 8.5 years. Imagine sending a question and waiting nearly a decade for an answer. Imagine transmitting a distress signal and knowing that no one will even hear it for over 4 years. By the time help could respond, nearly 9 years would have passed. In practice, there would be no help. No rescue mission could cross that gulf quickly enough to matter. A Mars colony waits minutes for guidance. An interstellar crew waits years and receives none. There is no resupply every 26 months. No cargo ship arriving with spare parts. No return window aligned by orbital mechanics. There is only the ship, the crew, and the silent interstellar medium. At some point, Earth becomes a memory rather than a partner. The mission transforms from exploration into separation. And this is where the tyranny of distance reveals its full character. It is not simply about propulsion. It is about autonomy. A Mars settlement remains an extension of civilization, delayed but connected. A voyage to Proxima becomes a departure without recall. Once launched, there is no turning back, not because we lack courage, but because the numbers make return effectively impossible. Distance does not shout. It simply stretches. It stretches energy requirements. It stretches time. It stretches communication. It stretches the very idea of belonging. And the farther we extend those lines, the more they begin to snap. Even if somehow we solved propulsion and energy, even if we built a ship capable of cruising at 10% of the speed of light and carrying enough fuel to slow down at the end, another challenge quietly waits inside the hull: time. 42 years in transit is not an abstract number. It is a human lifetime. A person who departs in their 20s arrives with gray hair, if they arrive at all. The metal walls of the spacecraft become the only horizon they know for decades. The stars outside never grow closer in any visible way. They remain fixed, distant, indifferent. The journey becomes less an expedition and more an environment. Humans evolved beneath open skies, with wind and weather and landscapes that shift. We are adapted to novelty, to social complexity, to movement across terrain. What happens when that terrain shrinks to corridors and compartments? We have hints. In 1972, a scientist lived alone in a cave for 6 months to study how humans perceive time without sunlight or clocks. Within weeks, his internal sense of duration unraveled. He believed far less time had passed than reality. His sleep cycle drifted to nearly 50 hours. He became depressed. And that was 6 months with the knowledge that the outside world still existed and that he would eventually leave. An interstellar mission would last decades. There is no exit hatch that opens onto Earth. Antarctic research stations offer another comparison. Crews live in isolation for months at a time, surrounded by hostile conditions. Studies show increased depression, anxiety, interpersonal tension. Submarine crews experience similar psychological strain during long underwater deployments. Even on the International Space Station, where missions last 6 months to a year, astronauts report mood shifts and conflict. Now stretch that timeline to 40 years. The same voices, the same faces, the same recycled air. Disagreements cannot be escaped. Personal conflicts cannot be walked away from. There is no fresh crew rotation, no quick return home. The group must be stable not for months, but for generations. Some argue that careful selection could solve this. Choose only individuals of extraordinary psychological resilience. Screen for stability, compatibility, emotional regulation. Perhaps that would help. But humans are not static. People change over decades. Stress accumulates. Relationships evolve. Even in the best conditions, conflicts emerge. And in deep space, conflict has nowhere to dissipate. This leads to the concept of the generation ship. If one lifetime is not enough, send many. Instead of expecting the original crew to endure centuries, build a vessel large enough to carry hundreds of people, sustaining a self-contained society that reproduces along the way. The people who launch the ship are not the ones who arrive. Each generation lives and dies aboard the vessel, contributing to a mission whose destination they will never see. This addresses the issue of individual lifespan, but introduces new constraints. Genetic diversity requires a population of at least several hundred to avoid inbreeding over centuries. Social stability likely demands more. The ship ceases to be a vehicle. It becomes a miniature civilization. Civilizations require governance, laws, education, healthcare, conflict resolution, cultural continuity. How do you ensure that technical knowledge survives across generations? The operation of life support systems, power plants, radiation shielding, these cannot be allowed to fade into myth. If expertise is lost, the ship fails. Unlike a nation on Earth, there is no neighboring country to trade with, no immigration, no external correction. Every problem must be solved internally, with the resources already aboard. Maintenance becomes an endless task. Every material degrades, seals crack, electronics fail, structural components fatigue. A spacecraft designed for 40 years might, with careful upkeep, last 80 or 100. But a voyage spanning centuries requires more than maintenance. It requires renewal. Parts must be manufactured in flight. Raw materials must be recycled indefinitely. Systems must be rebuilt from within the ship itself. Over time, the distinction between habitat and machinery blurs. The ship becomes an ecosystem of metal and biology intertwined. Radiation adds another layer. Interstellar space lies beyond the protective bubble of the sun's heliosphere. Galactic cosmic rays, high-energy particles from distant supernovae stream through the void. Over decades, cumulative radiation exposure would be severe. Shielding helps, but the most energetic particles penetrate meters of material and can generate secondary radiation when they strike shielding layers. Passive protection alone may not suffice. Active shielding, perhaps using magnetic fields to deflect charged particles, would demand enormous energy and engineering precision. Without adequate defense, cancer rates would climb. Reproductive health could be compromised. Over generations, genetic damage might accumulate. And then there is communication. A Mars colony experiences delays of minutes. Proxima Centauri sits 4.24 light-years away. A signal takes 4.24 years to travel one way. A round-trip message spans about 8.5 years. Conversation becomes historical record rather than dialogue. Advice from Earth arrives nearly a decade after being requested. News is ancient by the time it is heard. Emotional bonds strain across years of silence. Earth becomes less a partner and more an ancestral memory. By the time a generation ship arrives, centuries after departure, its inhabitants may share ancestry with Earth but little else. Language shifts. Culture evolves in isolation. Values diverge. They are human but no longer the same humans. The voyage does not simply transport civilization. It transforms it. The ship begins as an extension of Earth. It ends as something separate. Compare this with Mars. Mars remains connected. Resupply is possible every 26 months. Rescue, while difficult, is conceivable. Communication flows with manageable delay. Culture diverges but does not rupture. A Mars settlement is a branch of the same tree. An interstellar colony becomes a new tree entirely, rooted in the same soil of origin but growing alone beneath a different sun. The tyranny of distance is not only measured in kilometers and joules. It is measured in years of silence, in psychological endurance, in the slow evolution of identity. Turns a journey into a transformation. And the farther we look, the clearer it becomes that Proxima Centauri is not simply far away. It is separated by layers of physical, biological, and social barriers that compound upon one another, each demanding not just technology, but reinvention. Now imagine that, against all these odds, the ship survives. The propulsion worked. The reactors endured. The social fabric held together. The radiation was managed. After 40 years at 10% of the speed of light, or perhaps 85 years at 5%, the destination star finally brightens ahead. Proxima Centauri, once a faint red point among thousands, now dominates the forward view. The journey across nearly 40 trillion kilometers is complete. But arrival is not the end of difficulty. It is the beginning of a new set of questions. At cruise velocity, even 10% of light speed, you are moving at about 30,000 kilometers per second. At that pace, an entire planetary system would rush past in days. Without a deceleration phase equal in magnitude to the acceleration phase, you do not arrive. You pass through. To slow down, you must spend the same immense amount of energy you used to speed up. The rocket equation tightens its grip once more. Fuel must be reserved for braking. If miscalculated, the ship overshoots and vanishes into interstellar darkness, never to return. Suppose deceleration succeeds. The ship enters orbit around Proxima Centauri. The first detailed images of Proxima b fill the screens. It is likely a tidally locked world, one hemisphere permanently facing its red dwarf star, the other locked in eternal night. The day side may be scorched by stellar flares. The night side may be frozen solid. Between them lies a narrow band of perpetual twilight, the terminator zone, where temperatures might allow liquid water, if water exists at all. The star itself is volatile, known for powerful flares that can bathe nearby planets in radiation. Unlike Mars, which we have mapped extensively with orbiters and rovers, Proxima b remains known primarily through indirect measurements. We infer its mass. We estimate its orbit. We model its possible atmosphere. But we do not know its soil chemistry. We do not know whether it possesses a magnetic field. Without one, stellar radiation may have stripped away much of its atmosphere over billions of years. Without an atmosphere, there is no breathable air, no greenhouse warming, no shield from charged particles. The colony would depend entirely on artificial habitats from the first moment. Landing itself presents challenges. If the planet's gravity is higher than Earth's, as estimates suggest, those born in microgravity aboard the ship would struggle to adapt. Muscles and bones conditioned to weightlessness would feel strain. Even Earth-born crew, aged by decades in transit, might find the surface exhausting. Establishing a base requires energy, raw materials, and time. The ship likely carries supplies for a limited period, perhaps years, perhaps a decade. After that, survival depends on extracting local resources. If water is scarce, if useful metals are inaccessible, if radiation levels are extreme, the gamble of centuries becomes clear. There is no resupply fleet en route. No cargo ships scheduled every 26 months. No possibility of retreat. The distance that made rescue impossible during transit now makes return unimaginable. The colony must succeed or fade quietly into extinction beneath a red sun. Contrast this with Mars once more. Mars lies tens to hundreds of millions of kilometers away, not tens of trillions. Communication delays are measured in minutes, not years. Resupply windows open regularly. If conditions prove harsher than expected, missions can adjust. We know where the water ice lies. We know the composition of the regolith. We have decades of reconnaissance. Proxima offers no such familiarity. It is a destination reached through faith in models and telescopes. This difference is not merely quantitative. It is qualitative. Every metric shifts by orders of magnitude. Distance increases by roughly 700,000 times. Travel time expands from months to decades or centuries. Communication delays stretch from minutes to 8.5 years round trip. Resupply transitions from routine to non-existent. Rescue shifts from improbable to impossible. The nature of the mission transforms from exploration to separation. Even culturally, the divide deepens. A Mars settlement remains part of a shared civilization. News flows, art travels. People might one day move between worlds. Identity evolves but remains connected. An interstellar colony, separated by light years, evolves alone. Within generations, language drifts. Traditions adapt to local conditions. Memories of Earth become stories told in classrooms, then myths recited in ceremonies. The colony may begin as an extension of humanity, but over centuries it becomes something new. And perhaps that is the most profound aspect of the tyranny of distance. It does not merely challenge our engines. It challenges our continuity. Mars extends our civilization outward while preserving connection. Proxima demands divergence. It asks us to accept that those who arrive will not be the same as those who departed, not only biologically but culturally and psychologically. The act of crossing the void reshapes identity itself. In this sense, the physics wall is not only about joules and kilometers per second. It is about transformation. The farther we travel, the more the mission becomes irreversible. Mars is a difficult engineering project. Proxima is a generational commitment to becoming something different. One remains within the family of worlds we know. The other steps into permanent distance, where even light takes years to whisper across the dark. When you place all of this side by side, the contrast becomes almost serene in its clarity. Mars sits between 55 and more than 400 million kilometers away, depending on orbital alignment. Proxima Centauri rests nearly 40 trillion kilometers from Earth. The ratio is roughly 700,000 to 1. Mars can be reached in 7 to 9 months with chemical propulsion we already possess. Proxima, at our current maximum speed of about 0.07% of light, would require roughly 6,600 years. Even at 1% of light speed, a velocity far beyond our engineering reach today, the journey stretches to about 424 years. At 10% of light speed, the minimum that begins to resemble a human-scale expedition, the trip still lasts about 42 years, and that assumes we can solve energy production, propulsion, shielding, and deceleration all at once. Doubling speed quadruples energy. Accelerating a modest 100-ton spacecraft to 1% of light speed demands energy comparable to months of total human civilization's output. Pushing to 10% multiplies that by about 100. And then, upon arrival, the same energy must be spent again to slow down. The rocket equation does not negotiate. It demands fuel mass that grows exponentially. Chemical propulsion fails outright. Nuclear thermal improves performance but remains insufficient. Nuclear pulse propulsion could, in theory, reach a few % of light speed but faces political and engineering barriers. Fusion remains unmastered. Antimatter exists only in nanogram quantities. Laser-driven sails can send gram-scale probes at 20% of light speed. Yet they do not stop. They fly through and vanish into the dark. Layered atop propulsion is isolation. 40 years inside a closed environment tests not just technology but psychology. Studies of caves, Antarctic stations, submarines, and orbital missions suggest strain intensifies with duration. Extend confinement to decades and generations, and the ship becomes a floating society. It must manage genetics, governance, education, maintenance, and cultural continuity without external support. Radiation accumulates silently across years, threatening health and reproduction. Communication stretches into years-long silences. A distress call takes 4.24 years to arrive. A reply takes another 4.24. An 8.5-year round-trip delay transforms conversation into archival exchange. Earth becomes distant not only in space but in relevance. And then comes the final divergence. A Mars colony remains an extension of civilization. Communication delays are measured in minutes. Resupply is possible every 26 months. Rescue, while challenging, is conceivable. Culture diverges but does not fracture. People born on Mars may still one day visit Earth. The two worlds remain threads of the same tapestry. Proxima, by contrast, represents permanent divergence. There is no practical resupply, no timely rescue, no meaningful real-time dialogue. The colony becomes autonomous by necessity, evolving according to its own conditions beneath a red dwarf star. Within a few generations, language, norms, and identity drift. The connection to Earth becomes historical rather than lived. This is the tyranny of distance. It is not dramatic. It is mathematical. It is the accumulation of small, uncompromising realities. Energy scaling with velocity squared, fuel mass compounding through the rocket equation, light itself taking years to cross the gulf, biological systems straining under radiation and confinement, cultures shifting when separated by silence. Each factor alone might be manageable. Together they form a wall that is not easily climbed. Mars does not present such a wall. Mars is harsh, cold, irradiated, and thin-aired. It demands shielding, life support, in situ resource utilization, methane production through a Sabatier reaction, water extraction from ice beneath the regolith, supersonic retropropulsion to land heavy payloads of 20 to 40 tons, and an 18-month stay before a return window opens. It demands courage and funding and engineering discipline. But it does not demand new physics. None of its challenges violate thermodynamics or relativity. None require exponential leaps in energy production. None require decades of psychological isolation without hope of return. Mars is difficult. Proxima is transformational. When we say that Mars is within reach and Proxima is not, we are not dismissing ambition. We are acknowledging scale. One path continues the trajectory humanity has followed since the first satellite orbited Earth and the first footprints marked the Moon. The other demands breakthroughs not yet imagined, commitments spanning centuries, and acceptance that the travelers who depart will never truly return to the civilization they left. And yet, contemplating this vastness does not have to inspire despair. Can instead cultivate perspective. The universe is immense beyond intuition. 40 trillion kilometers is not merely a number. It is a reminder of the boundaries physics sets. Within those boundaries, Mars waits months away, not centuries. Minutes of communication delay, not years. Resupply windows measured in seasons, not generations. A place where we can learn to live beyond Earth without severing our connection to it. Perhaps one day propulsion will change. Perhaps fusion will become routine, antimatter manufacturable, or entirely new physics will emerge. Perhaps future generations will find ways to cross light years with tools we cannot yet conceive. But today, the contrast stands quietly before us. One destination extends our civilization. The other would divide it permanently. One is an engineering challenge. The other is a physics wall. If you are still awake, still traveling across these distances in your mind, gently type 2 in the comments. Let's see how many of us have journeyed all the way to the nearest star tonight and returned safely to the quiet red glow of Mars. When we move from physics and psychology to economics, the contrast becomes even clearer. A crewed Mars program is estimated to cost somewhere between $100 and $500 billion spread over several decades. That is a vast amount of money, but it is not beyond the scale of modern civilization. Spread over 20 years, it becomes perhaps $20 to $25 billion per year. For comparison, the United States alone spends roughly $700 billion every year on defense, and the global economy produces on the order of $100 trillion annually. In that context, Mars is expensive, but it is fundable. It fits inside existing political systems. It can be justified through science, technology, prestige, and long-term security. Interstellar travel operates on an entirely different economic scale. Concepts like Project Daedalus, a fusion-powered probe design from the 1970s, would cost in the trillions in today's dollars, and that was only for an unmanned flyby. A true generation ship capable of carrying thousands of people might require tens or even hundreds of trillions. That is not a national program. That is a civilizational undertaking requiring sustained global coordination for centuries. The investors would never see the outcome. The societies that began construction would not be the same ones that witnessed arrival. Mars can be attempted within a human lifetime. The stars demand patience measured in generations. This difference explains why Mars feels tangible while interstellar travel feels abstract. Mars has rockets under development, habitats being designed, life support systems tested, and clear launch windows every 26 months. There are engineers, budgets, prototypes, and timelines. Interstellar travel has equations, conceptual studies, and elegant renderings of ships that may never exist. One is a program, the other is a possibility. One fits within human political cycles. The other stretches beyond them. Still, the future is not entirely closed. Even if human starships remain out of reach, robotic exploration offers another path. Machines do not require air or psychological support. They can endure radiation more easily. A probe weighing a few hundred kilograms is far easier to accelerate than a floating city. Laser-driven sail concepts suggest that gram-scale craft could reach a significant fraction of light speed and cross the 4-light-year gulf in a few decades. They cannot yet slow down, but they can observe. They can gather data. They can turn distant points of light into map systems. Some thinkers imagine self-replicating machines that arrive at a star system, mine local resources, build copies of themselves, and continue outward. Over millions of years, such probes could spread throughout the galaxy. On human timescales, that sounds impossibly slow. On cosmic timescales, it is swift. The Milky Way is billions of years old. A few million years to explore it is a brief chapter. Even if humanity itself did not survive that long, something we created might. There is both hope and melancholy in that idea. Biology may also evolve in unexpected ways. Certain animals hibernate for months. Some can survive freezing. Tiny organisms can suspend metabolism almost entirely and revive years later. If human physiology could someday be placed in true suspended animation, long voyages would become psychologically trivial. Travelers would sleep through decades and awaken at their destination as if from a long night. We do not yet know how to do this safely, but history reminds us that today's impossibilities sometimes become tomorrow's routine procedures. The most radical possibility is digital consciousness. If the structure of a human mind could be translated into computation, interstellar travel would change dramatically. Digital beings would not require oxygen, food, or constant gravity. They could endure radiation, be copied, stored, transmitted. A probe carrying millions of digital minds might weigh less than a single human passenger. Yet this idea raises profound questions. Would a copy truly be you? Would continuity of identity survive translation? Technology might one day answer how to upload a mind, but philosophy will still ask what that means. Beyond the engineering lies a deeper issue: identity. If humans ever settle another star system, communication delays of more than 4 years one way mean that meaningful conversation becomes nearly impossible. A round-trip message would take over 8 years. Culture would diverge quickly. Language would evolve independently. Over centuries, even biology might adapt to local conditions. Interstellar expansion would not create a unified human empire. It would create branches related by ancestry, but separated by time and silence. Mars offers a different future. With communication delays measured in minutes rather than years, cultural continuity remains intact. Trade and travel, though difficult, remain conceivable. A Mars colony would feel like a distant province, not a separate civilization. Earth and Mars would share a story, even if they developed distinct identities. That is why Mars feels like extension, while Proxima feels like divergence. Perhaps a solar system civilization is the more coherent path forward. Earth, Mars, the Moon, and the asteroid belt multiple worlds connected by weeks or months of travel, but united by shared time. Not a fragmented diaspora scattered across light years, but a distributed yet continuous humanity. It may lack the dramatic romance of interstellar colonization, but it offers resilience without rupture, diversity without permanent separation. And so we return to something simple. Right now, photons from Proxima Centauri are reaching Earth. They left that star about 4 years and 3 months ago and have only just arrived. Our bodies cannot follow them yet, but our instruments can receive them. Our minds can interpret them. Knowledge crosses the gulf even when we cannot. The universe may remain physically distant, but it is not intellectually inaccessible. Maybe one day propulsion breakthroughs will narrow the gap. Maybe fusion will mature. Maybe entirely new physics will reshape what we consider possible. Or perhaps interstellar travel will remain an asymptote, forever approached but never fully achieved. History cautions against declaring permanent impossibility, but it also reminds us that progress unfolds step by step. The next step is not 4 light years away. It is tens of millions of kilometers at closest approach. It is 7 to 9 months of travel. It is difficult, dangerous, expensive, and achievable. Mars is within reach. If we learn to live there, to recycle air and water, to grow food under alien skies, to generate fuel from ice and carbon dioxide, we prove that humanity can survive beyond a single world. We build the foundation for whatever comes next, whether that is a thriving solar system civilization or, someday, something that reaches for another star. Perhaps we will stand on the surface of Proxima be one distant century. Perhaps we will not. But tonight, the achievable future glows red in our own sky. Mars is not a dream in the abstract. It is a destination. And every journey, even one measured in light years, begins with a step that can actually be taken. If you made it all the way from Earth to Mars, and outward to the nearest star and back again in thought, quietly type 3 in the comments. Not as celebration, but as a small signal, proof that before we cross the stars, we are already connected here at home. If we are honest with ourselves, Mars is not just a technical milestone. It is a psychological threshold. For all of human history, we have lived on a single world, protected by one atmosphere, warmed by one sun, dependent on one fragile biosphere. Every empire, every language, every invention has unfolded within that thin blue layer of air. To step onto Mars and remain there would mean that humanity is no longer confined to one cradle. It would mean that extinction, while still possible, is no longer guaranteed by a single planetary catastrophe. That shift alone changes the story of our species. The cost, though large, becomes more understandable when framed as insurance. We insure our homes against fire even if the probability is low. We insure our health even if we hope never to use it. A Mars settlement is a kind of civilizational insurance policy. Asteroid impacts, supervolcanic eruptions, engineered pandemics, runaway climate instability, these are rare, but they are not imaginary. A species confined to one planet is inherently vulnerable. A species established on 2 worlds gains resilience. Not immortality, not invincibility, but resilience. That is a powerful reason to attempt something difficult. But Mars is more than insurance. It is also inspiration. The act of attempting something so audacious reshapes culture. The technologies required, closed-loop ecosystems, advanced recycling, radiation shielding, autonomous construction, would feed back into life on Earth. Scarcity management on Mars teaches efficiency everywhere. When every drop of water must be reclaimed, waste becomes unacceptable. When energy must be generated locally and reliably, innovation accelerates. In striving to survive on a barren world, we may learn how to better care for the fertile one. Interstellar travel, by contrast, feels like a horizon that recedes as we approach it. Even if propulsion improves dramatically, even if we achieve 10% of light speed, the communication delay remains. For years one way, 8.5 years for a question and answer. Imagine trying to sustain a shared civilization under those conditions. News would be ancient by the time it arrived. Political debates would be irrelevant by the time replies were received. Culture would diverge not by choice, but by physics. The speed of light would become a barrier not just to travel, but to unity. That does not make interstellar expansion meaningless. It simply reframes it. Rather than a continuation of humanity as we know it, it becomes a branching. Separate societies, separate identities, perhaps even separate species over long spans of time. There is beauty in that vision. A galaxy slowly filling with diverse descendants of Earth. There is also melancholy in it. We would not share that future together. We would become stories to one another, distant ancestors separated by years of silence. Some argue that this divergence is inevitable anyway. Even without star travel, human culture evolves rapidly. Languages transform within centuries. Technologies reshape social structures within decades. The people of 1,000 years from now will be very different from us, even if they remain on Earth. Interstellar distances would merely accelerate that divergence. Perhaps continuity is always temporary. Perhaps change is the only constant, whether across oceans or across stars. Yet there is something deeply grounding about remaining within one solar system. Travel times of months rather than lifetimes. Communication measured in minutes rather than years. A solar system civilization could sustain exchange, collaboration, and shared memory. Earth and Mars might develop distinct identities, but they would remain in dialogue. The asteroid belt could host industrial outposts. The outer moons could become research stations. Humanity would be distributed but connected. That future feels ambitious without being alien. And perhaps that is the wisest sequence. Master life beyond Earth, within reach of the sun, build habitats that function independently. Develop propulsion systems that shorten travel times between planets. Learn how to govern societies separated by distance but united by shared time. Only after proving that we can sustain ourselves across millions of kilometers should we consider attempting tens of trillions. The path to the stars, if it exists at all, likely runs through the quiet mastery of our own neighborhood first. There is also a humbling lesson in acknowledging limits. Not every frontier must be crossed immediately. Some horizons exist to remind us of scale. The fact that Proxima Centauri lies 4 light-years away does not diminish us, contextualizes us. It reveals the immensity of the cosmos and the rarity of intelligence capable of contemplating it. The photons that left that star years ago and arrive here tonight are evidence that knowledge can travel where bodies cannot. We already participate in the wider universe through observation and understanding. So maybe the right question is not, will we reach the stars? But, who will we become as we try? If the pursuit of Mars encourages cooperation, innovation, and long-term thinking, it is worthwhile regardless of whether Proxima is ever colonized. If dreaming about interstellar travel expands our sense of possibility, it serves a purpose even if the dream remains distant. The act of reaching, even when the distance is immense, refines us. For now, though, the reachable horizon matters most. A planet that sometimes comes within 55 million kilometers. A journey that lasts 7 to 9 months. A challenge of engineering, funding, and courage, but not of impossible physics. Mars stands as a tangible next chapter. It asks for effort, not miracles. It demands persistence, not fantasy. Perhaps one day a child born on Mars will look up at a faint red dwarf in the southern sky and wonder about the worlds orbiting it. Perhaps that child's descendants will possess technologies we cannot imagine. Or perhaps humanity will remain within its solar cradle, thriving across multiple worlds without ever crossing the interstellar gulf. Both futures hold dignity. Both honor curiosity. For tonight, it is enough to recognize the difference between what is within reach and what lies far beyond it. The universe is vast, and we are small, but small does not mean powerless. It means deliberate, step by step, world by world. If you are still here, still traveling through these ideas, gently type 3 in the comments. A quiet confirmation that you have journeyed from Earth to Mars to the edge of the stars and back again, all without leaving your seat. There is a quiet kind of courage in choosing the achievable over the spectacular. It is tempting to focus on the most distant horizon, to imagine sleek starships slicing through interstellar darkness, to picture humanity scattering across the Milky Way like sparks from a fire. But progress rarely unfolds in dramatic leaps. It unfolds in careful increments, in systems tested and retested, in budgets negotiated, in prototypes that fail before they succeed. Mars belongs to that realm of disciplined ambition. It is not a fantasy built on unknown physics. It is a problem waiting for sustained commitment. Think about what it would mean for the first humans to land on Mars and remain there. Not flags and footprints, not brief visits, but permanence. A settlement where children are born under a thinner sky, where gravity is lighter, where the sun appears smaller. Those first generations would carry 2 identities at once. Descendants of Earth and pioneers of another world. They would celebrate holidays transmitted across millions of kilometers. They would speak in accents shaped by both heritage and habitat. They would still be human, still connected by conversation delayed only by minutes, still part of a shared unfolding story. That continuity matters. Contrast that with a settlement 4 light-years away. Even if a starship somehow arrived intact, even if a world like Proxima be proved marginally habitable, the colonists would step into isolation unlike anything in history. Every message from Earth would arrive 4 years after it was sent. Replies would take another 4. Conversations would span decades. Children born on that distant world would never meet anyone from Earth. They would inherit memories rather than relationships. Over time, traditions would shift in response to local conditions. Biology might adapt. Language would evolve. Humanity would not expand as a single thread, but branch like a tree. Branching is not inherently tragic. Evolution itself is branching. Diversity enriches life. Yet the emotional weight of permanent separation is real. There is something deeply human about shared time, about knowing that when you speak, someone hears you almost immediately. The speed of light preserves that intimacy within our solar system. Beyond it, intimacy dissolves into archive. This is why a solar system civilization feels coherent. It allows for growth without irreversible silence. The discipline of building on Mars would teach lessons essential for any future, interstellar or not. Closed-loop ecosystems must recycle nearly everything. Air must be scrubbed and regenerated. Water must be reclaimed. Waste must become resource. Energy must be reliable and locally produced. On Earth, we have often treated these systems casually because our planet is vast and forgiving. On Mars, there is no margin for neglect. Mastery of life support on a hostile world would represent a profound maturation of human technology and responsibility. It would mean we have learned to sustain ourselves deliberately, not accidentally. There is also a philosophical shift embedded in the act of settlement. For thousands of years, the night sky has represented unreachable mystery. To transform one of those wandering red lights into a place of habitation would alter our sense of scale. It would shrink the psychological distance between worlds. The moon already feels closer because we have walked there. Mars would feel closer still if cities rose on its plains. The cosmos would become less abstract and more personal. Interstellar travel, if it ever becomes feasible, will almost certainly depend on capacities forged in nearer challenges. Advanced propulsion may emerge from nuclear technologies refined for deep space missions. Autonomous construction robots tested on Mars may someday assemble components for starbound probes. Biological insights gained from long-duration planetary habitation may inform suspended animation research. Even speculative ideas like digital consciousness, if pursued, will draw on computing infrastructures built for terrestrial and planetary use. The path outward, if it exists, runs through the work done here and now. It is also possible that the universe imposes limits we cannot circumvent. The speed of light may remain absolute. Energy requirements for relativistic travel may remain prohibitive. We may discover that the practical ceiling for expansion lies within a few dozen astronomical units of the Sun. If so, that does not diminish our achievement. A civilization thriving across multiple planets, moons, and habitats would still be extraordinary. It would still represent one of the most remarkable transformations in the history of life. And perhaps the stars themselves do not require physical visitation to fulfill their role. They inspire inquiry. They motivate mathematics and engineering. They remind us that we exist within a structure far larger than any nation or century. The light from Proxima Centauri, traveling for more than 4 years before touching Earth, carries information about stellar flares and planetary shadows. We can decode those signals. We can learn without traveling. Knowledge expands even when bodies remain home. So the question is not whether the stars are worth dreaming about. They are. The question is whether we are willing to commit to the incremental steps that make any dream credible. Mars is one of those steps. It is difficult enough to demand seriousness and close enough to reward effort. It forces us to cooperate across disciplines, across nations, across generations. It asks for patience rather than spectacle. If humanity establishes a self-sustaining presence on Mars within this century, future historians may view that moment as a turning point equal to the first voyages across Earth's oceans. A second cradle, fragile but real. A proof that intelligence can adapt beyond its birthplace. From there, the options multiply, perhaps deeper into the solar system, perhaps someday toward the nearest star, or perhaps simply toward a richer understanding of our place among them. For now, it is enough to recognize that one destination is measured in months and the other in lifetimes. One can be attempted with technologies under development. The other waits on breakthroughs we cannot yet name. There is wisdom in choosing the reachable horizon first. And there is quiet optimism in knowing that the red planet shines each night not as a symbol of impossibility, but as an invitation. If you are still here, still reflecting on these distances and futures, gently type 3 in the comments. A small sign that even before we cross interstellar space, we have already begun the journey together.